Hello everyone, my name is Weber. From now onwards, I'm going to start a lecture series on the topic inverse T functions or inverse trigonometric functions, which is basically helpful for class 12 students for their board examinations. Now, before starting the session, let me just brief you some of the points. The first thing that you need to remember, I will be following the book by S.Chand Publications written by O.P. Malhotra. Okay. Next thing, if you have any other book followed by your school, then please do let me know in the comment section so that I would be considering the questions as well as the topics from that book as well. Okay, next thing. Now, one thing, let me just brief you in a very short manner. Now, if you are watching this topic inverse T functions for the very first time, then you would be able to deeply go through all the topics under this section. I would be deeply going through all the topics. Next, I would be doing all the solved examples. Next, all the practice questions would be done and all the chapter test questions. Next, and all the previous year board exam questions would be done with detailed solutions. So you need not to worry about the number of questions or the material. Everything will be provided to you. Just you need to watch the videos regularly. Okay. Next thing, whenever you watch the video, if you have any of the doubt, then just note down the timing, the doubt you have at that time in the video, and please put the comment in the comments tab. Then next time, whenever I will be posting the video, I will be just considering your doubt first of all, and then would be considering the session. Okay. So I hope I'm clear with all the things. So without wasting any time further, let's get started. Firstly, want to recall some of the points that would be beneficial for you throughout this chapter. So let's just have some points to remember. The first one, a relation. Do you know what is a relation? I hope you know, as this has been taught in this 12th class only. You might have read this chapter, but if not, then please go through this definition once, so in order to understand it more clearly. So basically, when I said the word relation, I just want two things. I just want the word set and ordered pair and nothing else. In terms of the mathematical terminology, I am saying this. So a relation is nothing but a set with ordered pairs, nothing else. Whenever I see these two things, I say it's a relation. Okay. Let's see this first example. R is equal to this curly braces, we have two pair, 1 comma 3 and 4 comma 3. Now, can I say it is a relation? Of course I can say. What I want, a set, which is denoted by these curly braces, and I want ordered pairs, which are these, one ordered pair and two ordered pair. So definitely I can say it's a relation. Similarly, I can say this is a relation. It contains three ordered pairs, 0, 0, 5, 9 and minus 1, 3, right? And it is a set that all these ordered pairs are contained in the set, na? So that means this is a relation. Clear? I hope the definition and the examples are clear. Now, before moving these two examples, let me just ask you a question. Now, whether these number of elements in the set would be limited, that means I can have a finite number of elements only or infinite as well. Think before you answer to yourself. Basically, let me answer then if you don't have an answer for that. So we can have an infinite number of ordered pairs in the set as well. And we will be looking at that examples as well. So consider this second example, which contain the ordered pairs x, y such that x and y are in W. Both are W. W means the whole numbers starting from 0 onwards. 0, then we have 1, then we have 2, and so on. Right? So these are whole numbers. And this is the important thing. How it is defined? It is defined like y equals to x to the power 5. So I defined the relation like this. Now, right now it's just a set with this property. Okay, I have to show that it is a relation. What I want a set which it is definitely no problem. I want it is a set of ordered pairs. Now it contains these bracket x comma y means the pairs. The ordered pairs are in this and these are relating like this. If I just ask you to write the elements, then it would be the first element because x and y are in whole numbers, so they start with from 0. So if I take x as 0, I can take, then just putting the value of x, what would be the value of y? Again 0. So 0 comma 0 is one element in this set. Another element, now another element can be if I put x is equal to 1, then what would be the value of y? Y would also be 1. So another pair is 1 comma 1. Now I can put x is equal to 2 as well. If I put x is equal to 2, then what would be the value of y? It would be nothing but 32. That would be 2 to the power 5. So, in a similar way, I can define the number of elements and it would be having an infinite number of elements, right? And they would be relating like this. Like I can put 1, 2, 3, 4, and dot dot dot, and so on. So, there are infinite number of elements. Infinite number of basically ordered pairs in this set. So, it is a relation as well. Okay, now look at this example. Now, this example is basically a generalized version of this second one example. Here, x and y are ordered pairs only. Now, x is relating like x equals to y to the power n for n to be in n. This capital N means the natural numbers. Now, you know that the difference between the whole numbers and the natural numbers. Whole numbers starts with 0 and natural numbers start with 1. Both goes in the same way, like 1, 2, taking the positive integers only. But only the difference is here in whole numbers we have 0 and natural numbers we just have starts from 1. Okay. Now, the relation is like this. X equals to y to the power n. Now, similarly, the elements are here. Now, n is a natural number and x and y are related like this. So, I can choose n. So, I can choose x to be any number. Right. So it is basically the generalized version. In this example, I put n equals to 5. That's why I get this pair. And here x and y are also limited. That means they are only whole numbers. Here we do not have any boundary for x and y. We can have any sort of x and y. That means x and y here I am having as the real numbers. That means I can consider any number x and y to define this relation. So it is again a set with the ordered pairs. So it is again a relation, right? So I hope so you are clear with the relation. And so on, we have infinite number of examples possible for the relation. Easy property. Just you need to remember relation means a set of ordered pairs. Nothing else. Clear? Okay. So let's now move to a next level. Let's move to a slide. A next. Now I define a special kind of relation called a function. What is a function? A function is also a relation, right? We want a relation, it is a relation, no doubt. Okay, so a function is a relation which has a special property. What? No two different ordered pairs can have the same first complement. That means if I just took any two different ordered pairs, I will not have to get the same first complement. Let me give you an example to illustrate this definition as well. Consider this example. Let R contain three ordered pairs 2, 5, 7, 3 and 0, 6. Alright. And S contain again 3, 4, 3, 1, 8 and 4, 7. Right. I need to verify whether these both options given to you are correct or not. Okay. First thing. First says both are relations. So in order to verify this, I need to first check the definition of relation. It must be a set of ordered pairs. Do I have this? So R is a set and which contain the ordered pairs only. True. So R is a relation. Now S is also a set which also contains the ordered pairs. So that means R and S are both relations. There is no doubt. That means first option is correct. Now, whether second option is correct or not, we need to verify this. That is asking about a function. So for the function, we must have a relation, and that is true for both R and S. Just we need to satisfy the second property, that no two different ordered pairs can have the same first component. Just pick this 2, 5 and 7, 3. These are different, right? Now these are different ordered pairs. Do they have the same first component? First it is having 2, it is having 7. 2 is not equals to 7. Now if I consider these 2, 5 and 0, 6. These are different ordered pairs and their first component is also different. One is having 2, another is having 0, right? I can also pick these two as well. 7, 3 and 0, 6. These are also different, but they do not also have the first same component. So that means this property is also satisfied for R. That means R is a function, right? It is a relation and satisfying this property, that if I just pick any two different ordered pairs, I do not have the same first. That means R is a function, it's guaranteed. So this half statement is correct, that R is a function. Now this is the part that we need to verify. While S is not, means while S is not a function. Okay. So again, I need to verify the second property only, because first one is already being verified in the first part. So just we need to verify this second property. Okay, so let me just start picking up any two different ordered pairs. Let me just pick 4, 3 and 1, 8. These are two different ordered pairs, right? They do not have the same first component because 4 is not equals to 1. Now I pick 1, 8 and 4, 7. These are also two different pairs and also they do not have the same first component. So up till now this property is verified unless I picked up these two. Now these are different ordered pairs, no doubt, but this is the problem creator, this 4. Now these ordered pairs have the same first component 4, and that contradicts this thing. Okay, that no, so I am getting 1. Okay, so I am getting this and two ordered pairs which have the same first component. So this condition is not satisfied. So that means it is not a function. So that means this statement is correct, that S is not a function, R is a function. So I can say both the statements are. Now, in case if I just put in place of 4 minus 4, if I just put minus 4, then they do not have the same first component. Although they have 4, but here we have plus 4 and here we have minus 4. Plus 4 is not equals to minus 4. I hope you know that, right? So just need to verify this second property for the function in this case. I get the answer. Okay. So I hope up till now you are all clear with the definition of relation and function, which is very easy and basic, as you also may have been known this. Let's now practice some of the questions. A quick short number of questions so that you can have a general confidence in you that you have known these two concepts very well. So first question, let R define this set x, y pair containing such that y equals to sine of x. First option, it is a relation. Second, it is a function. Okay. Second is S containing these three pairs and giving you these two options, whether it is a function but not relation or a function but not relation. And third one is this, t equals to the pair x comma mx, where m is in z. So here z means the integer, right? And giving the option that it is not a relation, and second, it is a function. So please practice these questions. Please pause this video right now, find out the answers to these questions, and then restart the video in order to get the correctness or confidence in yourself that you are doing it correct or not. So I hope you have done these three questions. So let me now reveal the answers. So these are the answers. Please match your answers. For the first one I have both of the options as correct. For the second one, none of these two options are correct. While for the third one, the second option, that t is a function, is a correct. I hope you get all the answers are correct. Then if not, then please watch this explanation. Let's now have some explanation. So for the first one, it is saying considering this set R which contain x comma y such that y equals to sine of x. I hope you have known up till now that this is a function basically. Sine of x is nothing but a trigonometric function. You may have been known to this. Now, in case you don't know whether it's a trigonometric function or not, so let me just draw its graph to have a clear understanding of how it looks like. It would be beneficial for you also. So let me just take some of the values of x and draw its graph. So I have taken these values of x like 0, pi by 6, pi by 4, for which I know the values of sine of x easily. Right? I know these values, that for these values, the sine of x values, I know this. 0, half, 1 by root 2, root 3 by 2. You might have learned these values earlier. So that's not an issue. Now we would be looking at the graph of this function y is equal to sine x, and we'll see whether it's a function or not and how it is a function. Okay. So first thing before starting, let me tell you, it is a relation firstly because it contains the ordered pairs and it is a set. So relation concept is clear. Now what I want is just that for any two different ordered pairs, it must not have a same first component, and that would be verified by the graph. Let's draw the graph. So basically on plotting the number of points that is drawn on x-axis, I would be getting the graph like this, which is y is equal to sine of x. So now if I just take, because these are the ordered pairs only, if I just take any of the point, I would be getting this x coordinate and the y coordinate, which is nothing but a pair. Ordered pair are like this only, right? First thing you need to believe, this graph is bounded. That means I can only go the maximum value of y as 1 and the minimum value is minus 1. The graph did not go above that and not below minus 1. First important point you must remember. These are the points that you must know about this function sine of x, because these will be important for you. Second thing you need to note, it is a periodic function. Periodic function. Now what is a periodic function basically? So periodic function is nothing but a function which repeats itself after a certain period of time, right? Like our earth is a periodic function. If it is a function, then our earth is a periodic function because it rotates around its period. That means it comes back to its own axis after a certain period of time, right? Similarly, the sine function, you can see at minus 2 pi and at 0, it is having the value 0. And as I just increase the value of x, then it traces back the same curve from 0 as well and goes the maximum at minus 3 by 2, minus 3 pi by 2 and also at pi by 2. Similarly, on further moving, it decreases and similar happens over here as well and assumes the value 0 at x equal to pi and x equal to minus. Then goes in the negative direction and similarly here. So it basically goes from here to here. So this is the path of the function up till here. After that, it again follows the same path on, and after that also it again follows the same path only. So it is basically a periodic function. First thing. Now we have a term called period. Period is not the class period that you would be having in the school. It is basically of a function if I just consider. So basically a period denotes that after how much time the function would be tracing its path again. Like this function if I consider, so it just traces back its own path after this length from minus 2 pi to 0. After this period of time, it traces back its own path. Now what is this distance? Distance is always positive. So I go from 0 to pi, that means 0 to 2 pi. So that means after 2 pi period of time, it traces again its path. Similarly, if I just look at here, so it meets up over here at something about 2 pi. So again the period is 2 pi. The period would be only 2 pi. It's not gonna change. It's not gonna change. The period is not gonna change for sine. And similarly for the cos function as well, we will be considering that cos function graph some other time. But for this time, this is the graph of sine function, which is periodic. It's bounded between minus 1 and 1, and its period is also 2. Now, I hope you get this thing clear. Now let me just come through the question what we are considering it for. We want to show whether it's a function or not. We have already shown that it is a relation, no doubt. Now consider this. Let me consider any two different ordered pairs. Suppose this and this. Okay. So these are two different ordered pairs. If I just consider them, this and let me just consider this. Both have different images, but we do not have the same first component. First component means the points on this x-axis. If I just consider any point, do I have two different images? No, I just have a single image, right? I do not have that if I just consider this point that I have image at this point as well and this point. So that these both are having the same image. So this is not the case over here. It's a continuous graph. That means it is just going on. It's not like repeating itself. It's not like it's going like this, then coming back this. If the graph would be like this, then at this point, I would be having two different images. One is this and another is this. So then I would be saying that this is not a function. But in the sin x graph, it is not the case. So thus it's a function and a relation as well. So thus both of the options are correct. Okay. Just replace this sin x term over here by cos of x. Then would the answer be changing? That means I would be saying that it is a function but not a relation. Something like that. Because the relation is always be there. Because of this set and ordered pairs. So no doubt for that. So would it be a function or not for the cos x? Please pause the video right now. Think of this and then replay the video. Well, the answer to that question is also yes, it is a function as well. Cos of x is also a function. Again, we have the three properties over here. First, it is a periodic function with period 2 pi. Okay, it traces back the same curve after 2 pi period. Second, its maximum bound is also 1 and minimum as -1. The same thing I can write like this, bound. And third thing, it is also a function. Okay, so second one was this set S which contains these three pairs, -5 to 1, 2 and 8, 2. Okay, so let's just verify. There are two methods to do this question. One was the earlier that I just given you, that compare any two pairs and just then see. Another method is I am not telling you, which is easy one, the second one method. Okay, so just look at this. Consider an egg or a bowl. Now I place the first components of these pairs in this egg, -5, 1 and 8, right? Consider another egg which contain the second pair. Now here all the second components are the same in each one, 2, 2. That means I wanted 2. Okay. Now this -5, 2 I can actually map like this. That means I can like -5 is related to 2, right? Similarly, 1 is also related to, because we have the pair 1, 2 as well. And similarly, 8, 2 as well. Okay. Now, this is basically the first components and these are just the second component. Okay, as I just told you. Now it is easy to just look at whether it's a function or a relation only or what it is. It is clearly a relation, no doubt, because it's a set containing the ordered pairs. So it is a relation, no doubt. Now the question is of a function, whether it is a function or not. So if I just having this a pair and its pre-image or -5 is mapped to 2, 1 is mapped to 2 and 8 is mapped to 2. I say that it is not a function when I have this thing. That suppose if I have another image 0 over here and I mapped it like this. So this is not the thing to be happen. That now 0 and 2 have the same pre-image -5. Then it would not be a function. But here it is only having one image and it is not having the same pre-image. It is having different one. Okay, let me have, suppose I have another element over here like 3 and this 8 is mapped to 3 like this and it is also mapped to 2. Then it would not be a function because now 2 and 3 both have the same first component 8. Correct? If I would be having not this line but would be having just this -5 mapped to 2, 1 mapped to 2 and 8 mapped to 3, then it would be a function because now 3 is having a first component is 8, 2 is having 1 and 2 is having also -1. First components are not the same for any two different ones. Correct? If this method is not clear, then you may look at the first method that I just told. Basically, you may have learned these things earlier. That's why I'm telling you. And this is basically a named function. And this is named as many one function. Right? A many one function. Now, can you tell why it is called a many one function? Anyone? Okay. So basically it is called a many one. The meaning suggests by the name. Many one means many have the many elements have the same image. Like minus 5, 1 and 2 have the same image 2. So many elements have the same image. It does not mean that all have the same pre-image, all have the same image. Like suppose if I have over 3 and I have suppose like 2 and this 2 is mapped to 3. Then can I say this is a many one function? Yes, I can say this is a many one function because I have this thing many images, many elements mapped to 1. It doesn't matter whether I have an element which is mapped to a single one. It doesn't matter. But if I have this one condition, then it is a many one function, right? You also have studied one function. Basically, these are just the opposite. If the function is one, it can't be many one. If it is many one, it can't be one. Just the opposite of each other. Now, in case you don't have studied this chapter, relations and functions, then I would be considering this chapter for the next time when we will be finishing off with this trigonometric function. Okay. Question was this. It was just saying, okay, this was a t, and it was like t equals to this x comma mx, m is in z. Z basically is the integer, right? Also written as I. Okay. Now clearly it is a relation, no doubt, because set with the ordered pairs. I want that thing only. Now I need to verify whether it is a function or not. Again, I'll be using the concept of graph and very easily you will be able to understand it. Okay. If I have to write this thing in a similar way, I can write it like this. Ordered pairs x comma y. Just remember how I am writing this. Look carefully such that y equals to mx and m basically belongs to z. I can also write this thing as this as well. Just look at the thing. How two set can be look like a different. You might be saying that this set is look different than this, but it is not. I can define the relation like this as well and this as well. Both means the same. So it is having this thing y equals to mx. It is also a very famous graph of straight lines. So just look at the difference in the graphs that I am drawing for y is equal to mx for different values of m, because m is an integer. So it can either be negative or positive or 0. But it must be an integer. Suppose m equals to 1. Then what will be the graph? Then we would be having y equals to x, right? And it would be looking like this. A straight line. When I put x2, y would be 2. x4, y would be 4. X minus 2, y minus 2. That means a straight line like now. If m equals to 2, then the graph would be looking like this. This was the graph for y is equal to x. And this is the newly one graph of y equals to 2 into x. Right? This is the graph. As I just increase the value of m, the graph moves forward. And here it moves down. Right? Just carefully note the difference how they are going. Suppose I again increase the value of m. Now the value of m is 3. Then it will be like this. Now for the first it increased up till this. For the now it is increased up till this. And this is the graph basically of y is equals to 3x. Right? Because m equals to 3. And here also it goes down. First it goes up till this. Now it goes still down. So it is going. Let's see more to have a clear image. For m equals to 4, it again moves forward. Now what you would be guessing for m equals to more higher values like 10, 11, 12 or 1000 or 10,000. Basically it would be this. On increasing the value of m, the graph would also be moving forward like this. These are all straight lines and it will be more clearing goes this and this, and at infinity, that means when m equals to infinity, it would be this straight line y equal. It would be straight line this y axis, and it would be going more and more closer to this y axis, more and more closer like this, and downward like this, more and more closer to this. So this is the graph that goes like this. If I just increase the value of m, so if someone asks you to find the graph of y is equal to mx of how it looks like, so you need not to draw the point. You just need to draw this y is equal to x, and you can tell that as I increase the value of m, it will go closer and closer to this y axis, right? I hope so. The graph is clear to you. Now I have a question. I just plot the graph for m equals to positive value. What if m equals to 0? That can be the possibility, right? Because it's an integer. So when m is would be 0, the graph would be y equals to mx, means y is equal to 0, because 0 into some number is always 0. Now can you draw this graph? It's pretty easy. It's nothing but the x-axis. That is the graph. So again you can see for m equals to 0 we have this. At 1 it increases to this. At 2 it increases to this. At 3 it again increases. At 4 and so on it goes on increasing and increasing up till it reaches this y-axis. So it's going like this. You can see this. Okay. Now, what for negative values of n? So n can be negative as well, na? Because m belongs to z, and z contains a negative as well, positive and the negative, right? So well, we have an answer for that, and the graph would be like for m equals to -1. It would be this. Earlier the graph was passing through origin, the 0, 0, and was like this. But now it just changes the rotation. It just changes and beats like this. That means you can say it's the mirror image along this y-axis, isn't it? If you just place the mirror on y-axis, then this line would be looking like this line. And that is exactly the thing, that y is equal to x is nothing but the mirror image of y is equal to minus x. Or conversely, you can also say, or conversely, you can also say like that y is equal to minus x is the mirror image of y is equal to x. This is the beauty of math. Right? So you just need to draw the graph of y is equal to x, and with that only you can be able to draw the graph of y equal to minus x. You just need to draw the graph of y is equal to 2x, and you can be able to draw the graph of y is equal to minus 2x by taking its mirror image. Just draw a graph like that. So it's quite an easy to look at the graph in this way. Again, now What for m equals to minus 2? Well, the same thing happens again. For m equals to minus 2 also, the graph moves like this. For minus 3, again moves ahead. That means it again goes in an increasing manner and going close and close to this y-axis for more negative values of m, as can be seen from this graph. And these are all just the mirror images of the previously drawn images, which was like this. You have to remember these graphs. So this is just the mirror images of each other. Clear? Now coming to the point of whether it is a function or not. Similarly, you can say straight line, any point would have any one ordered pair. It cannot have two images. So that means for any two distinct pairs, you would be having two distinct values of x and not the same one. That means you would not be having this kind of situation like this. That this point is also mapped to this and this point is also. You would not be having this kind of situation because these are straight lines, right? Passing through this point origin. And the equations are y is equals to m of x. Also, you can verify this with the help of the function definition in the general way as I taught you. Okay, so with the graph, you can directly and very easily say that for any point, you can have any one image of it, right? I hope so this thing is clear to you all, that for any one value of x, I cannot have two distinct values on the graph, right? So I hope so with these basic definitions, you will be clear off with the definitions of relations, functions, and examples. Okay? Now, an important question. What is the linkage between relations and functions? Or are they both independent? That means every relation is a function or every function is a relation. Which is true? Or none of them is true? Think before you answer. Just pause the video. Recall the examples that I have taught you up till now and then answer. So I hope so you get the answer. Let me just also tell you the correct answer is this one. Every function is a relation while every relation is not a function. First thing, every function is a relation. Definitely. Because if it is a function, then it must be satisfying the property of a relation as well. So that is definitely true, no doubt. Clear? Looking at this thing, every relation is a function or not. Now, in the starting, I considered an example. You remember? I consider the pair, like if I remember, 4, 2. Let us take 0, 0 and one more pair, 4, 3. Okay. Similar example I just constructed in the starting to explain the things to you. So here it is basically a set by these curly braces and containing these three ordered pairs. So it is definitely a relation, no doubt. Now, whether it is a function or not. Earlier I told you just consider any two pairs. So if I just pick up these two pairs, 4, 3 and 4, 2. Both are distinct. That means different ordered pairs. But their first component is the same. This 4, I'm having the same first component. So that means it is not a function. And this is the example that every relation is not a function. It is a relation but not a function. But if I have a function, then that is definitely would be a relation. I hope so you would be clear with these definitions of relation, function, examples. I hope so it's all clear, right? So let's now have some assignment for you, some homework questions so that you can practice them at home. These are the questions. First one question, you have a set A of real numbers, and second thing, your R is defined like this. Then you need to say whether R is a function, and R is a function but a relation but not a function. So which one is correct? Both are correct or none is correct, you have to choose. For the second one also you are given T, a set. It's given, it's telling you it is not a function but a relation. So you have to state whether it's true or false. Then you have these 3 questions as well. Another set, and similarly the 2 true and false. So these are the 5 set of questions as your homework. Please do these questions. We would be discussing these 2 questions in the next video. Firstly, we will be considering these answers of these questions. Then we will be considering the session. Please do this at home. So with this note, let me just end this session now. So please, if you find this video helpful, if you just learned something, then please like this video, share this video and subscribe the channel. Please do these things. It would motivate me to make more such awesome content for you. Please do this thing right now, and we'll be meeting you again in the next video with the latest discussion. And now after this brief introduction in this video, now we will be considering the topic inverse t functions or inverse trigonometric functions, and we will be starting with them as well in the next class. Till then, see you soon.